Hello everyone. In this talk, we will discuss the generation of permutations. So, recall that in the previous few weeks, we studied the permutation and the combinations. And in particular, we know that for a set of n elements, there are n factorial different permutations in total. However, this description, in fact, is very rough. That it means you only know the number, the cardinality of the set of permutations, but you don't know what's the relation between them. Just like in our class, we only know how large the class is. We have 92 students, but we don't know who is who. Of course, each individual has different personalities. So if you want to be a friend or develop some relations among yourselves, then it's very important to know each individuals. So in this lecture, we will talk about a final property of permutations. On the other hand, in reality, we have the problem like how to generate all the permutations on computer. This is important so how to generate permutations on computer. This is important because it's widely used error detection, the connection, turbo codes, LTE. So, and also from this we people develop many interesting algorithms, which is not only used in this lecture, in this topic, they also used in some other scenarios. There are some very naive, not naive, but very basic algorithms. So first, algorithm A, so generation in lexicographic order. Lexicographic, I will not explain it too much. You can see what does it mean from the examples, and later in the next lecture we will study further and give a more rigorous definition for that. So suppose you have A0, A1, AM-1. So here, in this lecture, we will use this notation to mean a permutation, because in computer science, probably you are more familiar with square bracket. And also, we start with 0, same reason, because of the computer science. And just a small remark, this kind of method is known long time ago by Indian mathematician Narayana Pandita, probably in 14th century India. Probably some earlier work also know this, but the earliest I know is this Indian mathematician. Okay, so next we describe the steps for the algorithm. So the whole algorithm is like when you put in some permutation. If you run the algorithm once, then you get a next permutation. If you run second time, you get a new one again. And an algorithm is called generating permutation, is that we need to generate all the permutations without repeating. Okay, so we can look at this lexicographic algorithm. Generate the next permutation. Lexicographically after a given permutation. So first, find the largest index k such that ak is less than ak plus 1. And if no such k exists, then we stop the algorithm. We stop the program. In other words, the permutation we have is the last. Secondly, as soon as you have k, we try to find the largest index L larger than k, such that ST means such that in mathematics. You have different order. You have the same order. AK is less than AL. And thirdly, we swap the value of AK with that of AL. 4, we reverse the sequence from AK plus 1 up to and including the last element AN. Okay, now we look at one example. Suppose we start with 1, 2, 3, 4. So this is our A0, A1, A2, A3, the starting permutation. And if you run the program, so first, by the step 1, we will find k is 2. Right, because notice that the index is starting from 0, so k equals 2 means we choose this position 3, because you have for A2 equals 3, less than 4 equals A3. Okay, next, second step, we choose L equals 3 because A2 less than A3 and 3 is the largest index. Okay, then you run step 3. You need to swap the position. So this is your this is your K, this is your L. Swap AK and AL, which gives you 1, 2, 4, 3. And the last step, you need to we need to reverse AK plus 1, which is A3, to up to the last one, A3. Therefore, you keep it same. Okay, so after running once from 1, 2, 3, 4, we derive a new permutation 1, 2, 4, 3. Okay, now let's go one step further. We run it again, see what can we have. And then let's be sure. So in step 1 we have k equals 1 here. K, sorry. This is your k. K equals 1. Okay, and step 2, what is L? L is 3. This is your L. And you swap AK and AL. So you have this. Swapping A1 and A3. And the last step, you need to reverse AK plus 1 is A2 up to A3, the last one. So finally you have this one. Okay, therefore here, after you running one more time, you have this. And you can prove, I will not prove it. So this is a good algorithm such that generate all the permutations without repeating. And moreover, the last one is 4, 3, 2, 1. So a remark how to show this. I leave it to you. It's in your textbook. This is our first algorithm to generate permutations. Next, we introduce a different one, which is called a random generation of permutations. So the advantage of the lexicographic order or lexicographic algorithm is that when you do some proof or theoretical proof, this is very clear what is the next one and how to do induction. Just like you have dictionary, it's very easy to refer to some specific letter. But it also has some drawbacks. The first drawback, not only the lexicographic one, but also all the systematic generations, they all have this drawback, is that totally you have n factorial permutations. Okay, and then no matter how you do, this is a larger number. No matter what is your algorithm is, this is a larger number. By Stirling formula, this approximately equals square root 2 pi n times n over e to nth power. So for example, when n equals 100, so a set of 100 elements is not that large, right? In our class, we have almost 100 students. So it's not a very, very big or very weird number. But if you look into the permutations, you will find it's too much for the systematic generations. I just give you some number comparing to we only have 10 to 97 particles, elementary particles in universe. But of course, the n factorial when n equals 100 is larger than the number of particles, total particles. So it's a very huge number. And no matter how is this permutations, how is the algorithm is, it will never give you permutations for larger numbers. Okay, that's why why people raise up the random generation. For random generation, no need to assume that n is small. So whenever that's the idea for the random for introducing the randomness in mathematics or in science. Sometimes we sacrifice some accuracy to get some lesser or easier computation. Okay. So we introduce several algorithms. First one is very famous, Fisher-Yates Schaffer, 1978. So the aim is to give an algorithm for random permutation of a set 1, 2, 3, all the way to capital N. So I think if you major in statistics, you know Fisher is very famous and actually one of the founders of the statistics, and he also do fantastic work in the biology to explain how how cells or how animals develop some strategies, why we have sex ratio like this or that. So it's a big shot in science. Okay. So step 1, the algorithm is as follows. Step 1, we just write down 1, 2, 3, 4 all the way to n. And then you pick a random number. Okay, between 1 and n. And between 1 and 1 and the number of unstructured numbers remaining inclusive. We will see what does it mean just in a moment. And then counting from the low end, from the smallest number, strike out the case number not a struck out and write it down at the end separate list, and then step 4, repeat from step 2 until all the numbers are have been struck out. And then it turns out that then the sequence of numbers written down in step 3 or step 4. Step 3 is now a random permutation of the original numbers. Okay, so first let's do some remark. So here actually we make some assumption. That is, we suppose we make the assumption that the random numbers in step 2 are truly random. So here, the only place we use the randomness is this one. But I haven't tell you how to get the random number. Actually, there are a lot of pseudo-random generators. So we make the assumption that it's truly random and unbiased. So how to do this? Usually we use the pseudo-random generator. So you can tell from the name that it's a pseudo-random generator. So it just approximately unbiased. So actually, this is a very good question. Can we develop a method to derive the true randomness and von Neumann's opinions? Is negative. Anyone who considers arithmetic method of producing random digits is, of course, in a state unseen. And so far, no people have a truly random method. So whenever we see random, just idealize it. And in fact, we mean pseudo-random generator. There are a lot of pseudo-generator algorithms. So when you do computer program or coding, you just use some built-in functions. And remark 2. So in step 3, actually we have some drawbacks which can be improved. That in step 3 we spent needless time counting the remaining numbers. Okay, and therefore the time complexity is bigger O n squared. That means it develops or it increases like n squared. It's no more than a polynomial of degree 2. Okay, and later on, people know how develop some refined method to get rid of the needless counting. So we have the so-called the modern method or the Distenfeld Knudsen shuffle, and then the time complexity can be reduced to O(n). So it's just a linear bound. Okay. So the method is, let's do some setup to shuffle an array A0, A1, AN minus 1. We do for I from n minus 1 down to 1 to j. Choose a random number j such that j is between 0 and I, and then you exchange aj and ai. Yeah, this is from Wikipedia, and it's just a pseudo code, and it's better to understand it. Use the following example. So suppose we have 1, 2, 3, 4, 5, 6, 7, 8. This is our starting permutation, or set of 8 elements. Okay. So you will have the following table. So the first column is the range, and the second column is when you do the random algorithm, pick a random number, and the third column is a scratch paper, and the last one is result after running the method once. So when we start with the original 1, 2, 3, 4 all the way to 8, and then the range is 1 to 8. So you pick a random number from 1 to 8. For example, you do 6. Okay. Then for the scratch paper, you need to change 8 and 6. Sorry, change 6 and 8, and then just delete 6. So finally you have this. And for the 6, you just write down on the result paper. And next, the range is 1 to 7. You run the random algorithm, pick a number between 1 and 7. For example, it's 2. Okay, now you exchange the second number with the last one, and then drop 2. So you have 1, 7, 3, 4, 5, 8, and you put 2 in front of 6. And next we have 1, 2, 6. Suppose we have 6 again. Okay, now you need, because 6 is same as the last index, so you change 8 with itself. You just keep it. Okay, then you just drop 8 1, 7, 3, 4, 5, and put 8 in front of 2. And for 1 to 5, suppose we have 1. Okay, then you need to exchange 1 and the last one 5. And drop the last integer and put 1 in front of 8. Okay, and suppose you have 3 in the next step. And then you need to exchange 3 and the last one 4. And drop the last one 3 after you exchange. So you have this. Okay, 1, 2, 3. Next one, suppose you have 3, and you exchange it with itself. You have 1, 7, 4, 3, 1, 8, 2, 6, and now you have 2 numbers. You pick 1 randomly, and then you drop first one. Sorry, you first do exchange and then drop the first one. You have 7, 5, 4, 1, 8, 2, 6. And the last step, you just, because you only have one choice, so no matter how random the algorithm is, you choose 1. So you have 7, 4, 5, 4, 1, 8, 2, 6. So running the program, the random generation tells you that now you have this as a successor. Oh, sorry, I missed 3. Oh, this is right. So you have 7, 5, 4, 3, 1, 8, 2, 6. Of course, a remark is you running, different people may have different answer running the program once. Okay. Different results. This is a big distinction between the random method and the deterministic method. For example, for the lexicographic method, no matter how you run each step, after each loop, you will always have the same result, no matter who you are, no matter which computer it is. But for the random method, even you use the same computer program, because of the pseudo-random generator, you may have different answer. Okay, and here we still have some unsatisfactory issue, just like every time you do too many changes from permutation to its immediate successor. And we hope that can we have some method use the minimal changes, just like do 1 permutation. Sorry, just change 2 numbers. Two elements for each permutation, and its immediate successor. So the answer is yes, and there are many methods. We introduce one, which is called Steinhaus-Johnson Charter algorithm. Next, we also give another famous heap algorithm. So to do this algorithm, we introduce an actual geometric structure, which is called arrow. So given an integer k, we assign a direction to it. So you can either assign it k point to left or k pointing to right, and then consider a permutation of 1 to all the way to n, in which each of the integers is given a direction. K is called mobile. If its arrow points to a smaller integer adjacent to it. For example, we have the following assignment of arrows to the permutation 2, 6, 3, 1, 4, 5, 4. And then you can see that 6 is mobile and 3 is mobile. 5 is mobile. Okay. Then the algorithm can be given as follows. We begin with the most mobile one. That is, each element is mobile. And you can prove this is unique. Unique permutation with assignments such that each element is mobile. So if there is a mobile number, if there's no mobile number, just as we said before, we are done. That will be the last one. So find the largest mobile number. M, second step, switch M and the adjacent integer to which its arrow points. Sorry, it's a Lunar New Year. Okay, and Happy Chinese New Year, Ox. This is second step. Okay. And then we switch the direction of all arrows above integer p with p greater than m. Okay, now for example, this is also a deterministic method algorithm. Suppose we start with 1, 2, 3, 4, and then you can see the largest integer we have with which is mobile is 4. Then first you exchange 4 and its adjacent element to the direction of arrow 3. Okay, next the largest is still 4. Then you do exchange again to have 1, 4, 2, 3. And then similarly you have 4, 1, 2, 3. Then next you have the largest mobile one is 3. Then you have 4, 1, 3, 2 by exchanging 3 and 2. Okay, and now we don't do switching elements, because when we run step 3, we do have integers larger than 3, also the larger than 3. Therefore we use different color. We need to switch the arrow instead of the element. Okay, next, when we run the program, you find the largest element is 4 instead of 3. 4 is mobile again. So 1, 4, 3, 2, and then 1, 3, 4, 2. Okay, and you can keep on going. For instance, let me do one more. 2, 4. Okay, then next you do 3 again. 3, 1, 2, 4. But then you need to exchange the arrow above 4. Okay, keep on going. I will not give the proof that this is a good algorithm that generates all the permutations without repetition. If it is so trivial, then it will not have 3 names on it. Okay, I also leave it to you. Either you can find it in your textbook or from Wikipedia. The next very interesting algorithm is called Hipper's algorithm. So for Hipper's algorithm, we don't need to introduce the arrow. The idea is easy. It's like following. So for n plus 1 objects, first permute the first n objects and then interchange the content of the n plus 1's cell with those specified cell in the first n positions. And what does a specified cell mean? It means that if n plus 1 is odd, the specified cell is the first one. Otherwise, if it's even, it is number consecutively from 1 to n. And it looks like you don't know how to generate it, how to expect what is the next one. But for computer, this is an easy algorithm because, and the idea is also very important in computer science because you can do induction. So if we draw a picture, how to understand this algorithm. Suppose you have n plus 1 elements from 0 to n. Okay, and so first you always fix the last element n and do permutation. All permutations of the first m elements. And of course, when you study the first n elements, you also fix the last one and permute the first n minus 1 elements. So that's a so-called induction. I will give you an example to illustrate this. And then after you're done with all permutation in the first n positions, then next one, depending on the parity of n plus 1, now you need to exchange n with some number inside, for example, m0. Okay, after you fix m0, then you can run the program again, and which generating all the permutations of the first n elements. Okay, and so suppose this is the last one, m0, and blah blah you have. Okay, next, use Hippos algorithm. You can pick out some unique number m1 to replace m0. You do the exchange m0 with m1 and then run the program again. Okay, and finally, since the last position can only be integers from 0 to n, so the last, no matter how the intermediate step is, last one will be m minus 1. Okay, after you change with, m minus 1, after you change with m minus 2, and then you generate all the permutations of the first n elements. Then we are done. Okay, and I will give you an example. So suppose we start with 1, 2, 3, 0, 1, 2, 3, 4, 5. Okay, and you want to run the program, you find first inductive, you need to change the first two elements. So next one you have is 0, 1, 0, 2, 3, 4, 5. Okay, and then this is these two are the permutations of two elements. Okay, then you need to exchange. You need to change 2. And notice that now 1, 0, 2 totally has 3 elements. That is odd. Therefore, you need to change 2 with the first element. To pick out an integer for the last position. So you have 2, 0, 1. Okay, then you run 0, 2 again. And then since 3 is odd, you change 1 and 0. You have 1, 2, 0, 2, 1, 0, 3, 4, 5. Okay, and now you have 6 permutations. That's all a permutation of 3 elements. Then you need to make some change of 3. So how to do 3? So for 3, you need to change with first element, and then second element, then third element. Okay, so first you change it with 2. That gives you 3, 1, 0, 2, 4, 5. And then you go back to the 3 element and do the permutation. Okay, so you have 1, 3, 0, 2. You do this. You have 0, 3, 1, 2, 4, 5. 3, 0, 1, 2, 4, 5. And then you have this. You have 1, 0, 3, 2, 4, 5. 0, 1, 3, 2, 4, 5. Now totally you have 6 permutations for 3 elements. That's all. Then we need to change the position of 2. Since 4 is, why is 4? Because so here n plus 4 equals, n plus 1 equals 4 elements. It's even. And the first step, we change the last one with the first one. Exchange with first one. The first position, sorry. And therefore here you need to exchange with the second one. That is, you need to exchange 1 and 2. Okay, then you have, 0, 2, 3, 1, 4, 5. Okay, then you run the program again. 2, 0, 3, 1, 4, 5. And 2, 0, 3, 1, 4, 5, and we start here 3, 0, 2, 2, 1, 4, 5, 0, 3, 2, 1, 4, 5, and you do this. You have 2, 3, 0, 1, 4, 5, 3, 2, 0. Okay, then you are done with the first the permutation of 4 elements whose last position is occupied by 1. Now you change 1, and then by the algorithm exchange with the third position, third 1. That is, you need to change 1 and 0. Okay, therefore you have 3, 2, 1, 0 as the immediate successor. Okay, then you have similarly 6 permutations. And now you have to exchange 2 and 3. So 2, 1, 3, 0, 4, 5. 1, 2, 3, 0, 4, 5. Okay, after this step, we are done with the permutation of 0, 1, 2, 3. We need to introduce 4, element 4. So by the algorithm, we know that n plus 1 is 5, and therefore 4 has to be changed with 1. So you have 4, 2, 3, 0, 1, 5. So you can keep on going, and totally you expect 120 permutations, right? Okay. And a very interesting question, what would be the last one? Okay, I will stop here, and the next time we will talk about how to generate combinations and some partial order relations.